You can start. Yeah.
Hi. So my name is Luis. I'm a PhD student at the Technical University of Madrid, and today I'm presenting this work on generation and refinement of testing models. So first, I will give you some context. Testing is probably the most widespread technique to check software quality, and is especially important in dynamically typed programming languages. And property-based testing is a great technique, which is based on logical properties across inputs. As our friend John Hughes here in the audience usually says, it consists basically in not writing tests, but generate them. So this is an example of how property-based testing works. For example, if we want to test the identity function, we would generate random inputs, and we will check some property, in this case, that the generated inputs are at the same, after applying the identity function, we get the same result. So now I will introduce you to the API that we are going to use during this presentation. So normally when we want to test APIs, we write what we will call scenarios or test cases. For example, here we have this API which has two functions, a function to create lists and a function that inserts values into the list. Notice that we are going to use an API for working with sorted lists. So both the results in both, especially in insert, must be a sorted list, and also the argument list in insert also must be a sorted list. Here I draw I made a figure with the graphical representation of the execution of one of these tests. We have these three commands, and after the execution of each command, we will check some postcondition, some predicate. So how do we generate this kind of scenarios and test these APIs? In property-based testing, we usually use what we will call testing models, which are basically specifications of these APIs, and they deal with three concerns: a way to generate sequences of commands, a way to execute them, and then they have the information to check some postcondition after executing every generated command. So, for example, usually the property that we check when we test these models is that given a model M and a program P, for all the commands defined in this model, after running them, everything must go properly or must be okay, right? So after the execution of these tests, we would assume that the program behaves like the model. So the motivation for this work is that, using these testing models is a proven technique. We have many papers that prove that test real-world systems and found bugs in them. Our recent research has focuses on improving these testing model languages. Especially, we've worked on this library called Makina, which is open source and is available in that link, that introduce mainly two features to these testing models. First, a declarative syntax that help us avoid certain kind of common mistakes, and also introduce some composition and refinement operations. So the key idea of this talk is, these models are still very difficult to write. So the idea is don't write models, generate them, but this time from simpler specifications, okay? So let's dive into what we mean by simpler specifications. So here I introduce you a simpler specification language. We introduced this Corsa library last year, which introduced the sign by contract in Elixir. And basically, we are going to focus on 3 kinds of contracts. Basically, preconditions that make requirements of a function explicit, postconditions that ensure some properties on the result of the contract, and specs that can be thought as pre- and post-conditions focus on types. Also, Corsa is an open source library, and this is the link where you can download it and try it. So here in our insert function, we have this precondition that the input function must be sorted. We have this postcondition that the result function should be sorted and its length must be incremented by 1 after inserting an element. And we have this spec that tells us that the types of the function. So let's see how this works, what happens when we call insert. So if we call insert with a list which is not sorted, it will throw an exception that tells us that the precondition does not hold. And if we call it with a sorted function, it behaves like we expect and it computes the result. So now I will proceed you to introduce you to Makina, which is the model language that we are going to use during this presentation. So Makina is a domain-specific language embedded in Elixir, which is can be used to write these testing models. In Makina, a model consists of 2 things, basically a state that has some attributes which contain a name, an initial value, optionally some type annotations, and a set of commands where each command has a name, a list of parameters, also optionally type annotations, and some callbacks that restrict the generation, tell us how to generate some arguments, and deal with how to update the state of the model and how to check some property. So here I have an example of a model in which we tell which program we are going to test by using implemented by, which is an option in Makina. This is the state definition, which has an attribute list with an initial value and some type. And it has also 2 commands, the command that is going to call or new function that creates new lists and insert. And basically here we have this component, these callbacks. The precondition is the one that restricts the generation of commands. Args is the way that we generate arguments to this command. Next tells us how we update the state after executing each command. And post is the property that we are going to check after executing this command. In this example, we are going to check that the result of insert is sorted. So here I have also a graphical representation of how we execute the model. So we start at the initial state. We take the set of commands that have a true precondition. That are the ones that tell us that we can generate that command. After that, we execute the updates of the state, and if there is some postcondition, we also check it. Okay, it's not. So let's see. Let's introduce Faktory. Faktory is this new tool that we are presenting in this work, which is basically what we're going to do is generating these models from programs which are annotated with Corsa contracts. So here in this figure we see how it works. It's really simple. So how we do this generation? Well, in the generated model, each command corresponds to a public function in the annotated program. And this model that we are going to generate is stateless. Okay, so here we see that we have our annotated program, which has new and insert, and is using the Faktory tool, and generates automatically this model that has these two commands. With this model, now we can execute sequences, random sequences of our API. So now, how we generate command arguments? So we are going to derive the arguments generators from the specifications of our functions. Basically, here I have some code that explains how we do it. First, we extract the abstract syntax tree from the argument type. We translate it from Elixir, from the Elixir abstract syntax tree to Erlang, and then we use proper to obtain a generator for that type, because proper already has this notion of how to generate values from types. Notice that with this way of generating commands, we could generate lists that will not pass our precondition contract, because we are not generating sorted lists, we are just generating lists of integers. Okay. So this is a problem, because as we have seen, when we generate these kind of values, when we call the implementation, it's going to throw some exceptions. And in property-based testing libraries, these exceptions are understood as errors. So this is a problem, because it's not really a problem in our implementation, but it's a problem that our generator is not good enough. So we took this decision that we will capture all the exceptions when we call the implementation. So this way we can reason about them in the postcondition of the model. Okay. So now let's see what is the postcondition of the model. So as we are using contract annotations, the correctness property after executing the function is already encoded in the postcondition contract. So we don't have to do anything in our model. Our model just needs to throw an error when this postcondition fails, and ignore the results when the precondition or the specs throw some exception, because as we said, is because our generators are not good enough. So here we have some execution results which are a bit disappointed, because well, we've made a lot of calls to both functions here in our API, but nearly 90% of our executions fail to pass the precondition checking. So the problem is that, of course, our generators are not good enough. So here we see an example of a sequence that our model could generate, where the second generated command will not pass the precondition, so it will be inserted, it will be ignored. So notice that the first one will be executed, the third command will be also executed correctly, but the second one is ignored. So this is where all this 90% is coming from. So how can we improve data generation? So well, the obvious way or the traditional way would be to write a generator for sorted lists. But this is a manual task, and well, it's not really easy also to generate this kind of data. So let's recall our API. In our API, we have two functions, one that constructs data from the API, and another function that modifies this data. So the idea we are presenting here is why don't we reuse the results of our operations to generate valid data? So what we're going to do is to store valid results in the return by the API, so we can at least have the chance of improving our results on precondition check-ins. So to do that, so we introduce the random option in Faktory, which is a number that ranges from 0 to 10. And this random option modifies the distribution of arguments generated during the tests. For example, if this option is 5, approximately 50% of the calls will use the type-derived generator, and the rest will use previous results. Notice that only this will be applied to arguments whose type matches a type which is returned by the API. And this is how it's used. So now, how Faktory works in this case is, when we annotate random, we will generate two models. The model that derives that we have seen, that derives generators from the type specs, and another one that is going to store this state, the previous results in the state. So this new model, as we have said, extends the previous one using the Makina refinement option. And this is useful because like that we don't need to redefine all our previous behavior in ask, call, and post. And this new model just adds a new attribute in the state, which is called instances. That is basically a map that will store every result that our API will generate during the execution. So, all the results are stored in the model state just by updating this map. So we introduce a next callback in all the commands in the model. And finally, here I show you how we generate arguments, which is it's a bit confusing, but basically what we do is we extract the types, the values of that type stored in the state, and if we have any values in that state attribute, then we randomly generate with a certain distribution between we randomly choose between the type generator and the type derived generator and the results in the state by using the random option that we introduced before. So we showed that we were using 5, and this will be like half of the values derived from the type and the rest from the state. And if we don't have any value stored, so we will use just the type derived generator. So here I show you some execution results where we can see that by using this heuristic, or the number of precondition errors is diminished a lot. So these results are much better. Still, we have like 30%. Probably, if we have more functions in our API, this number will be lower. So, but what if we just reuse previous results? So we have another option in Faktory, which we called opaque. That appear because sometimes it's really hard to get a generator for certain types of values. For example, ETS references, which probably if we generate them randomly are not going to be valid references. So the idea of opaque is that it forces the use of previous results and receives a list of the types that are going to be just used from these previous results. And the usage is like that. We just pass those types in a list. So again, this is what Faktory does. It generates these two models. It looks like the previous figure. Well, this new model works exactly like the previous one. We reuse all the implementation on the previous one, and we introduce this state which contains the previous instances. And basically, we introduce a precondition because if we try to generate a command without having values of a needed argument in the state, the generation is going to fail. And when this is the code for generating arguments. This time we only use previous values, as I said. So here I show you some difference and interactions between random and opaque. Basically, because of this pre that we have added, when using opaque, the sequences that we can generate are restricted. So, for example, the first one could be generated, but the second one is not possible to generate it from the model. And also, well, as I've said, when using opaque, the model never reuses the type-derived generators. And notice that when a type is annotated with opaque, and it appears in an argument, but is not produced by other commands, this command is not going to appear in the sequence, but, due to this precondition that I've shown you. And if a model uses both random and opaque, the type is going to use the opaque. Opaque overrides the behavior of random. So here we have some execution results. Now we are able to generate tests without contract precondition errors. But we see that due to this precondition that we have added, we call like 500 times new, but just 400 times insert. And new is not a really interesting operation in this case. So how can we improve this? Well, we have Makina extension, the Makina extension operator. So we could write a new little model that modifies the weights of the generated commands. When we talk about manually write these models, we don't mean that you have to open your Emacs and edit some weirdly generated file. We just introduce this. We just use extends and write a new module. And notice that in these new modules we could modify the distribution of commands, or we could add new post condition, or even we could merge multiple generated models using the composition operators in Makina. So this is the work. The key idea again is don't write models, generate them. And I have presented the Faktory tool, which generates executable models from contract annotations. I showed you different options to tune the automatically generated models, and also think that we can use these generated models as initial models that can be further refined. This tool is also publicly available in that link. And as future work, we have seen some limitations of the contracts in Corsa because this specification language doesn't allow us to talk between relations between commands in an API. So this makes it really difficult to generate good test cases. So maybe we could improve this language, like, I don't know, something like session types, linear temporal logic, something like that. It's open. We're still not working on that, but maybe it's a nice thing to have. Also, another idea that appeared during this work is to reuse valid generated values between different runs. For example, this could help us to test our API in this example with really long and big lists. And also, we could improve generated models with, for example, static information to improve the coverage of the test with something like concolic testing or something like that. And that's all. Thank you for listening.
Thank you so much for such a great talk. Do we have any questions? Yes.
So when you reuse previous values, are you reusing any previous value of that type generated during testing, or are you reusing previous values from the same sequence, the same test case?
It's just from the same test case, yes. Now, currently it's just from the same test case.
So that makes sense to me, because in some cases, especially when you use opaque values, the values you generate may represent some kind of resource that has been created. But something else that is quite a common situation is that resources may be both created and destroyed.
Yeah.
And then you shouldn't perhaps really use them after they've been destroyed.
Yeah, that's right.
Do you have a way of handling that?
Well, not yet. No, we don't have that capabilities, but also because we don't have any way to specify that in the Corsa language. If we have this kind of, like, I don't know, like some temporal logic that we forbid a command after destroying or something like that, maybe we could create that kind of sequences, but now we are not able to do that. Yeah.
Of course, some of the tests most likely to be failed might be the ones where you do try and reuse a resource that's been destroyed.
Yes, also, yes, that could be. Yes, of course. Thank you.
Do we have any more questions? I do have one small question. Have you tried to use this on some part of the Elixir standard library? And if
well,
so,
in the paper we have 3 examples, and we use it to test the queues which are in the standard library, and also some part of the ETS system. Yeah.
And how much manual work do you need to do to get good results, or is it?
Well, it depends on what you call by good results. Just by adding this use factory annotation, and you have something executable, but you need to add like these specifications with pre and post conditions to have some sense of what is going on there.
Right, but if I were to add the pre and post conditions and I have the type specification as well, right? Mm-hmm. Will I see more often than not like these 30% of preconditions that are not satisfied, so therefore it's not valid in a way, or?
Well, yes. Well, so, it depends on the API you are testing. You can like play with these options of random and opaque, and to try to get. It's really easy to change it. So, yeah.
Great. Thank you so much.
Yeah. Well, you wanted to
question?
Yes, I had one more question, which was this idea of reusing previous values is something that Randup also did. Mm-hmm. I wonder if you can say anything about similarities or differences between what you're doing and what Randup did.
No, I don't. Random, just like I don't. Random.
Oh, there is a tool called Randup, which was developed for object-oriented programming languages.
I don't know that.
It would be a good idea to read that paper then.
Okay, thank you.
Thank you so much.
Thank you.
So we proceed now with the